For almost a century, it was basically a ghost in the quantum machine. A phenomenon that was predicted on paper, but was pretty much considered impossible to actually see in real life. It was a scientific mystery that spanned generations. But now, after an 87-year hunt, that ghost has finally been caught.
We tend to think of quantum mechanics this way, don't we? As this really abstract thing, this set of rules for a world we can't ever really see or touch. But the story of the Migdal Effect, well, it proves that with enough patience and, let's be honest, a whole lot of ingenuity, even the most slippery quantum predictions can be dragged out of the equations and right into the real world.
And wow, what a wait it's been. This story kicks off way back in 1939, right on the brink of World War II, with a really bold prediction. Then nothing. An 87-year-long silence where the effect was thought to be unobservable. And it all culminates in 2026 with a breakthrough that changes, well, everything. So what exactly were scientists hunting for all this time?
Okay, so let's set the scene. It's pre-World War II Leningrad. A Soviet physicist named Arkady Migdal comes up with this radical new idea about what happens deep inside an atom during a very specific, very sudden kind of collision. The idea itself was elegant, it made perfect sense on paper, but for the better part of a century, it would remain just that, a ghost, a theory. So how does this whole thing work? Well, to get your head around the Migdal effect, you need to picture an atom a little differently. Not as a tiny solar system, but more like a single unit. You've got the dense nucleus at the core, and then this cloud of electrons that's bound to it. Migdal's big question was, what happens if you suddenly kick the nucleus, and only the nucleus? Well, this is what happens. The Migdal effect is what you get when a neutral particle, we're talking something like a neutron or maybe a dark matter particle, slams into an atom's nucleus. The key here is that it's a sudden approximation. The kick is so fast, so incredibly abrupt that the electron cloud just doesn't have time to react. It kind of gets left behind. Let's break it down. You know that classic magician's trick with the dishes on a tablecloth? If you pull the cloth out slowly, the dishes just move right along with it. But if you yank it out with incredible speed, the dishes stay put, right? Inertia. The Migdal effect is the quantum version of that trick. A neutral particle hits the nucleus, that's the yank. The nucleus recoils instantly, but for a tiny fraction of a second, the electron cloud is just left hanging there. And in that moment of confusion, there's a chance that one of those electrons gets shaken off and just flies out of the atom.
Okay, so if the theory was so clear, why on earth did it take 87 years to actually see it? It's because looking for the Migdal effect was like one of the biggest needle-in-a-haystack searches in all of modern physics. It was a massive challenge.
The first big problem was just the odds. They were terrible. For every 10,000 times a neutron smacked into a xenon atom's nucleus, the theory predicted the Migdal effect would only happen once. You're looking for an exceptionally rare event inside an interaction that's already happening on a microscopic scale. And it wasn't just how rare it was. The universe is an unbelievably noisy place. The signal from a Migdal electron would be so tiny, and it would be completely drowned out by a constant shower of cosmic rays from space and even trace amounts of natural radioactivity in the detector materials themselves. For decades, it was just impossible to build a detector quiet enough to hear this faint quantum whisper. But that all changed down at the Panda X4T experiment, which is this massive detector buried deep underground to shield it from all that noise. Scientists finally did the impossible. They built a machine that was sensitive enough and quiet enough to finally catch the ghost. And their strategy was just brilliant. Instead of looking for just one signal, which, could just be noise, they looked for a unique two-part signature, a smoking gun that could only be the Migdal effect. They needed to see two things happen in the exact same spot at almost the exact same time. So here's what that two-part signature looks like. First, you get signal number one, a tiny flash of light from the nucleus itself as it gets kicked by the neutron. That's a super low energy event. Then, right after, they'd look for signal number two, a second, totally separate signal created by that shaken-off Migdal electron as it travels through the liquid xenon. Finding both of those tracks coming from the exact same point, that is the undeniable proof. So after sifting through millions upon millions of events, they found 6 perfect candidates. 6! And the statistical significance hit what's known as 5 sigma. That's the gold standard for a discovery in particle physics. To put that in perspective, it means the chance of this result just being a random fluke is about 1 in 3.5 million. The ghost was real.
So they found it. An 87-year-old prediction is finally confirmed. That's a huge deal for science, obviously, but what does it actually mean for us? Why does catching this one quantum ghost matter so much? Well, it turns out it gives us a brand new tool to hunt for something even bigger and even more mysterious.
And here is why this is so incredibly important. The Migdal effect basically acts like a natural amplifier. See, we think the universe is full of invisible dark matter. Now, if those dark matter particles are really light, they would only give an atomic nucleus a tiny, almost undetectable little kick. But here's the cool part. That tiny little kick can still trigger the Migdal effect, shaking off an electron that creates a much larger, much more visible signal. We're not just listening for the faint kick anymore, we're listening for the loud echo it creates. And that right there is a total game changer. With the old methods, our detectors had a really high energy floor, which meant we were completely blind to any low-mass dark matter particles. But by looking for the Migdal effect, we can dramatically lower that floor. It opens up a whole new frontier in our search for the universe's missing matter. It's huge.
So a prediction made all the way back in 1939 has given us a brand new way to explore the cosmos in the 21st century. It took 87 years of relentless innovation to find this one little quantum effect hiding in all the noise of the universe. It really makes you wonder, right? What other secrets are out there, hiding in plain sight, just waiting for us to build the right tools to finally see them?